thanks everyone for coming back. Let's continue. So yeah, last thing I was saying, you could have solved it using a truth table. That's also okay. Simply at the end, you have this and you have this. They're not equivalent because, for example, when this is true, this is false, and so on. I think now you're pretty seasoned with truth tables. Exercise 4. The idea might be similar to exercise 2, but here we're going to be using set identities. So I don't think we're going to be relying very much on going to that x belongs to b and so on and so on. So for example, in the first one, a minus b minus c, is it equal to a minus b union c? Actually, they said prove everything, so it should be fine. I mean, you should just be proving, you're not going to be disproving anything here. So a minus b minus c. What's that? It's just the elements in the first set intersecting with the complement of the other. Same thing for inside. A intersecting with B complement. We know it's associative, so take the brackets to B and C complement. De Morgan, what does this mean? Just elements in A that are not in B union C. So let's see parts B, C, and D quickly if there's any trick to them. Because I think they're simply going to be using everything you know from the normal propositions, the distributive law, commutative law, but now it's using sets. So yeah, here it's just distribution. Yeah, maybe we rely here on double complement and De Morgan's a bit more than the first part. So yeah, if anybody faced a problem with these parts, let me know and I'll go into detail, but they seem easy enough. Let's check part D, just because it looks interesting. So is A intersection with the A intersection with the universal set? What's that? It's just going to be A. A intersecting with the universal set is just going to be A. Union B intersecting with phi, nothing. This is going to be phi. That's A. Okay. Fair enough. So using identity and domination laws. Deal. Exercise 5. Let's do some functions. Find the domain and range of these functions. So what's a function? It goes from the domain, let's say, to the range. Should be something like that. Like what's x? Is it students? Where do you take that student? The function that returns the number of ones in a bit string. So a bit string is just a string made up of zeros and ones. So that's going to be kind of like our domain here. So the domain is going to be strings that are made up of zeros and ones. It returns the number of ones in a bit string. So if you have a bit string, 0, 1, 1, 0, 0, 0, and so on, the function takes the string and it's going to return to you how many ones you have here. So for example, we have 4 ones. What's the least number of ones we can have? 0. What's the most? There is no maximum. You just keep going, keep going. So you keep going. This is the set n. So a function f from b to n, where b is the set of binary strings, that is to say having binary numbers, sure, that is, they only have zeros and ones. Okay, fair enough. The function that assigns to a bit string the number of bits in that string. Same thing, we're going to be taking a bit string, but this time we're going to be returning the whole size of the string. So you're counting zeros and ones. It's going to be the exact same thing. Same thing. Last one, the function that converts a number from decimal base 10 to binary base 2. So here decimal, they don't mean decimal like 3.5 or like the points system. It's base 10. Base 10, this is what you use in every day, what you use in your life. Like if you're gonna count the number of items you have in your room, you're gonna go 1, 2, 3, 4, and it's gonna look like this: 1, 2, 3. Okay, you reach 9. When you add one more item, it's gonna be 10. So 10 system. You have 0 till 9 digits. So you have 10 digits, base 10 system. Whereas binary, we only have 2 digits, 1 and 0. So when you're counting in your decimal, when you reach 9, okay, now you're gonna start with the 10th. So now it's gonna be 10, 11, 12, till you reach 19, 20. So 9 is like your maximum before you have to start going to the left, building something new. With binary, no, you have 0 and 1. So let's start counting. 0, 1. I can't go more than this, so now I have to start going to the left. 2. Okay. 3. I can't, this is the maximum, I can't keep going. So now I have to go to the left again, but this is also the maximum digit here again. So this is 4. Okay. So 0, 1, 2, 3, 4. So it depends really on what planet you're from. If you're from the planet Earth and you show this to somebody, he's gonna tell you 10. If you're from a planet where you only have one finger on each hand and you show someone this, they're gonna say that's 2 if they work in a binary system. But this wasn't the point of the question at all. What's our domain and what's our range? Let's convert a number. So the number could be negative. So I noticed they had z integers going all the way to b, which what we defined. So yeah, in binary, you might be saying, hey, I'm going from negative to, how's that? In binary, there's a representation for negatives using just ones and zeros too. You could add a minus, but not necessary. Exercise 6. Give an example of a function z to n that is 1 to 1 but not onto. 1 to 1 but not onto. Okay. So again, 1 to 1 means injective, onto is surjective. Let's just check some of the examples they made. So 1 to 1 but not onto. What does that mean? For any xy, if x is different from y, then that means f of x is also different from f of y. So any two elements here are going to be pointing to two different elements here. But they're saying not onto, so you could have an element here, C, that doesn't have anything pointing to it. So they gave you this, and 0, they're saying, has no pre-image. So it's not onto. In other words, you can't give me an x that will make this equation as 0. You can check. You can try some numbers, like try if x is -2, -1, 0, 1, 2, 3. You'll notice, and after you keep going here and increasing x, it's just going to get bigger. The other way around is just going to get smaller because it's negative. And yeah, there's no area where it's going to be 0. Yeah, I mean the f of x isn't going to be 0. Onto, but not 1 to 1. Onto, but not 1 to 1. So they're saying f of x equals the absolute value of x. So this is just kind of like a v. So usually it's just, usually if you didn't have an absolute value, so if it was the function f of x is just x, it'll be like your main bisector, or whatever this is called, the main division in this graph. But now, since we have an absolute value, whenever x is negative, the y is going to be positive. So it's actually this, sort of like a v. A parabola also works. So you notice for this x and for this x, you're going to have the same y. For every x, maybe. Yeah, for any x, for the v f of x equals f of minus x. Okay, cool. Both onto and one-to-one, but different from the identity function. I think they might be saying different than this. And they give you an example. It's both one-to-one and onto. In other words, it's bijective. It's similar to part A, yeah, but here, if you say f of 0, it's going to give you 0. So 0 does have a preimage. Seven. Okay. This symbol is the ceiling. So I mentioned it in the recitation. If you're like in a room and you have 3.5, 3.6, and so on, the ceiling of 3 point something, it's like you go all the way up till you reach the next integer part, like in the ceiling of your room, which is 4. Whereas if you keep going down, 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 you reach the floor. So another symbol is saying, hey, the floor of 3.5 is 3. So the least, so the smaller integer part. Okay. Show for all the real numbers that this is true. Oh, prove or disprove. So it might be or it might not be true. Hint, for every real number, it can be written as 4q plus r, where q is in z and r is either 0, well, it's anything between 0 or 4. It's not just 0, 1, 2, and 3, because r is in the set r. So it could be a decimal, the normal decimal that we know. This symbol, if it doesn't remind you of anything, it feels like an element that's divisible by 4, right? 4q plus something. It's not, if it was just 4q, then it would have been divisible by 4. So in other words, if r was 0. The reason I think why they said, hey, use 4q plus r, because the biggest divisor you have here, or the biggest denominator, is 4. If it was just 2, they would have said, hey, use 2k plus 1 and go with it. Okay, so in this part, I feel we're just going to be plugging it in and see what we get. Yeah. So for starting with the left-hand side, yeah. The left-hand side, just plug it in. What can we have? 4q over 2 is going to give me 2q. This you can bring it outside, because 2q is going to be now, like it's an integer. So the ceiling of 2q or the floor of 2q is just going to be the same, because it's just an integer. Plus r over 2. Okay, q again with 2, and it goes outside because q is an integer. We're left with this. We can't do really anything with r just yet because, hey, r can be anything here. So if r was less than 2, it will make a difference if r was greater than 2. On the right-hand side, we got this. So now you have to ask yourself, are these equivalent? You have to run through all the cases in R. Let's see how they did that. Case when x or r or whatever is 0, it's true on both sides. It's just going to be q. All this is 0, goes away, q equals q. Now they're saying everything between 0 and 2 strictly greater than 0 or less than or equal to 2, it also works. Why? So x is less than or equal to 2. So the ceiling of this is always going to be 1. Then the ceiling of half is going to be also 1. For the other side, x over 4, it's like 0 point something. Ceiling is 1. They're the same. We're left with the last range, which is x is between 2 and 4. Same thing. Now x over 2 is going to be 1 point something, because x is strictly greater than 2. But it's strictly less than 4, so it's 1 point something, not 2 point something. Ceiling of 1 point something is going to be 2. 2 over 2 is 1. Done. Right-hand side, same thing. It's equivalent. So yeah. Exhaustive proof. So you're checking every possible case in the range 0, 4. Okay. Part B and Part C. Oh, a lot of information in this assignment, right? Part B, when I first looked at it, feels like it's not going to be right. Because radical can really downsize your element. And yeah, they use the counterexample. Just go through this, use the counterexample, so it's not going to be right. Part C is very interesting and slightly hard, so take a breather and let's try to do this. So is the floor of x plus y, the floor of y, plus this, is it less than or equal to this for all real numbers x and y? Okay. Step 1 is, hey, let x be a plus alpha and y be b plus beta. So in other words, we want to take out the integer part and just leave the decimal, like the point something. As you can see, alpha and beta are the point something, if this was a decimal number. So step 1, substitute x and y with the definitions we just said. The a's and b's can go out. Alpha and beta has to stay inside. Well, you'll notice here you have 2 a's and 2 b's, so you can just cross them with this. You're left now with the actual thing you're trying to prove, is the floor of the decimal parts of our numbers. Again, we're gonna have to go over every possible proof. They're saying we have 6 cases, but it can be reduced to 4 without loss of generality. We'll see what they mean by that. First case, what if both alpha and beta are less than half? Remember, they're between 0 and 1. What if they're both less than half? You can already see why we have 6 cases, right? If they're both less than half, if they're both greater than a half, and then this and this, this and this, and the other ones. So if they're both less than half, then their summation is also going to be less than half. So the floor of this is 0. Again, alpha is less than half, so 2 times alpha is going to be less than 1. Floor is 0. Both sides, so 0 is less than or equal to 0. That's true. What if they're both bigger than a half? Well, if you sum them, they're going to be greater than a 1, but still less than 2, because both of them are less than 1. The floor of that is going to be 1. Right-hand side, it's going to be 1. 1 is less than or equal to 1. Okay, nice. Now we reach the without loss of generality. So they're both less than half. Oh, sorry. So 1 is less than half, alpha, and beta is bigger than half, but the summation is bigger than 1. You can see here, without loss of generality, you could have said, hey, beta is less than half. and alpha is bigger than half. Would have done the same result. What we care about is this part. The summation is bigger than 1. Okay. Well, alpha plus beta, it's going to be between 1 and 2. Why? Well, because that's just the given. Here we're assuming alpha and beta are bigger than 1. They're still going to be less than 2. Floor is 1. 2 alpha is going to be 0 because it's less than half. 2 beta is going to be 1 because it's bigger than a half. 1 is less than or equal to 1. Same thing, but now their summation is less than 1. And again, you could have flipped this and flipped this. So this flipping is the 2 other cases that without laws of generality. Their summation is less than 1. Floor is 0. Again, 2 alpha is less than 1. Floor is 0. 2 beta is bigger than 1. So the floor is 1, but that's fine because 0 is less than or equal to 1. So for all the cases, again, exhaustive proof, it works. Hooray. I think the rest of the parts are going to be more. If you have any problem with part 7 or the previous parts, let me know. They were very proof heavy. Now I think it's going to become a little less, let's say, strict. Let f of x be this, g of x be this. Determine for which constants, a, b, and c, and d, this is true. So step 1, you just have to write it. F round g of x, it's going to f of g of x. So simply here in this x, you have to put all of this and expand. Whereas g round f of x, the other way around. F, you put it in this x. Okay. Exercise. Sorry, now we see what happens. Sorry, do you have a question, Samir?
هبعرف عن حاجة. لا المهم هاي جاي ظبطها يقول في نوت جاب تيجي معنا شو
Okay, I guess not. So this is f round g and g round f. When are they equal? When this part equals this part. Just to make the equation better looking, we take the d here and the b on the other side, take each in common. You're left with this equation. So for example, if you set d equals b, like if the equals 0, then for whatever value of a and c, both sides are going to be true. So yeah, it's not just like one constant, hey, take a is 1, c is 2, and so on. There might be infinite many possibilities. Okay. 3 more questions, we're almost there. Exercise 9. Give an example of 2 countable sets, uncountable sets, A and B, such that A minus B is this. Now, uncountable set, it just means it's not countable. So you can't find a bijection from the set N to the set you're working with. Well, for the finite, you could just choose the set to be the same. Let's see what they did. They said, hey, A is R and B is R minus 0. So A minus B is going to be just the element 0. The size of this is 1. It's just one element, so it's finite. But if you chose, hey, they're both the same, it's still going to work. You get phi. This phi is finite. You just have 0 elements in it. With countable infinite and uncountable infinite, I think they use the same trick. So You want two uncountable and you get a countable. So hey, just r and r without n. They're both uncountable. When you subtract them, you're going to be left with n. Like you're removing everything from r except n. Same thing for the uncountable. R and R without 0, 1. You're left with 0, 1. Or you could have said, hey, R is A, B is 0, 1. A minus B is just going to be R minus 0, 1, which is also uncountable. A lot of different examples. Exercise 10. Determine for the following, which sets are finite, countably infinite, uncountable. If it's countably infinite, exhibit a one-to-one correspondence between the set of positive integers and that set. One-to-one correspondence, it just means it's bijective. It means it's both injective and surjective. Both one-to-one and onto. The negative integers, yeah, that's countably infinite, right? So we have to exhibit a one-to-one correspondence between it and n. Simply, hey, to negative integers, I'm just going to say minus n, but that's not really a proper symbol. So 0 to 0, 1 to minus 1, 2 to minus 2, and so on. Yeah, that's what they did, but they added a 1 here. So I'm guessing they assume 0 does not belong to the negative integers. So that's fine. So it's kind of like 0 goes to minus 1, 1 goes to minus 2, and so on. If you did either way, it's okay, because usually 0, is it negative, is it positive? It's under a lot of discussion. The odd integers, same thing. It's countable infinite. 0 goes to 1. 1 goes to 3. 5. It's kind of like you're always skipping the even, and so on. So it is countable infinite, and that's mapping. And there it is. So if n is even, sorry, yeah, that's correct, the odd integer. Oh, yeah, that's correct. Because they said odd integers. So the odd integer could either be negative or positive. What I did was, this is for the positive odd integers. But integers could be negative or positive. So for example, 0 goes to, let's say, 1. Then you have 1 goes to minus 1. 2 goes to 3. 3 goes to minus 3, and so on. See how that works? So if it's 0, f of 0, 0 is odd. No, 0 is even. So you'll get minus 1. Okay, so minus 1. 1 is positive. Oh, sorry, 1 is odd. So f of 1 is just 1. And so on. 2 is even. Minus 2 minus 1, you get minus 3. And you keep going. The integers that are a multiple of 7. So 7k, just 0. I get, let's say 0, 0, in case they assume 0 is a multiple of 7. 1 goes to 7, 2 goes to 14, and so on. Yeah, it's just f of n is 7n, multiples of 7. The integers are positive. Okay, so positive, we just wrote 7n. If it was negatives and positive, we would have had to do something like part B. Integers that are not divisible by 3. So 3k plus 1, 3k plus 2. It's like you're skipping the multiples of 3. And I don't think that's hard to do, right? Let's say 0. Let me write that again. 0, 1, 2, 3, 4, 5, 6. Keep going. Assuming 0 is a multiple of 3, you want it. Sorry, it's not a multiple of 3. You don't want it. 1 is not divisible by 3, so you take it. You take 2. You skip the 3. You take 4. You take 5. You skip the 6. It's a multiple of 3. You take 7. You take 8. You get the idea? Like you take 2 consecutive digits or numbers, and then you skip the multiples of 3. And 0, 2, 4, that's even. Then you have 1, 3, 5, that's odd. So you can break it down into, hey, if n is even, then f of n is going to be what? 3k plus 1. Like the remainder is 1. If n is odd, it's going to be 3k plus 2. So the 4, the 8. Yeah, so that's what they did. Map numbers of the form 3k plus 1 to 2k, and 3k plus 2 to 2k plus 1. In other words, we split in half. 3k plus 1 to even numbers, 3k plus 2 to odd numbers. I don't know if they didn't write the function because it might be messy, but they explained it pretty well. Are they all countably infinite? Positive multiples of 4. So it's, again, it's just, I think it's 4k, kind of like part C. Odd negative integers. Odd negative integers. Kind of like part B, but without the positives. Okay, great. Finally, part G, it's not countably infinite. Positive numbers that are less than 1 million. It's going to be something that's finite. Countably finite. Okay. 4 into n plus 1. So they're assuming 0 is not a multiple of 4. Positive, no, that's not. Odd negative integers, okay. So I'm getting the feeling that with multiples, they're assuming 0 is not a multiple. It depends again on the course, the definition, how the university takes care of it. So make sure you ask your professor about that. Finally, exercise 11. Almost there. It's not the longest assignment that we've had to go through. I feel in previous assignments, we went longer. I think we've been going for like 55 minutes or maybe less. But it's heavy on a lot on proof and reading. So I get your frustration if it's a bit wordy. Prove that if A and B are sets, A is uncountable, A is in B, then B is uncountable. They're sets, A is uncountable, and if A is in B, then B is uncountable. This is actually the rule of a pretty good rule that will do you well. If you have two sets, A and B, and let's say A is subset in B, if you know that B is uncountable, sorry, if you know that A is uncountable, then B is also going to be uncountable. But before we can actually use this rule or law, we have to prove it. Well, in the recitation I mentioned, hey, if you want to prove that something is countable, you just have to find a bijection from n, from the set n to this set you're trying to prove that is countably infinite. If you're trying to prove that something is not countable, Well, you have to prove that there's not this. There's not a bijection, or for example, there's not, there's not a bijection. Okay, so how do you do that? Assume that there is. You assume there is, you get a contradiction. So what we will do here, assume that B is countable, so you do have a bijection and something that is going to explode. Assume B is countable, so if B is countable, then there exists a bijection between B and N. So you have N. Okay, so they want to do the bijection like this, from B to N. Why not? Now they're going to construct a function f of A by restricting the domain of F. So kind of the elements that are in A, we're going to just be like focusing on these mappings. Instead of focusing on the whole set B, we are only going to look at A. Remember, B to N, that's a bijection. So it's both injective and surjective. Okay, we created, okay, so this is, let's say, f of B. We created a smaller f of A. What do we know about it? Since f is injective, like f of B, since f is injective, then f of A is also injective, right? What does it mean to be injective? You already know. Obviously, B is injective, so A also has to be injective. Like you're not gonna find two different elements in A that point to two different elements, sorry, that points to the same element in N. Because otherwise, B wouldn't be injective. But it might not be onto anymore. That's fine. However, A is uncountable, then there does not exist any injective function from it to N. If you didn't know this, like it's a property. If a set is uncountable, there is no injective function. Obviously, definitely there's no bijection, but there's definitely no injective function. But with your assumption, you just did do that. You did find an injective function. So we have a contradiction and B must be uncountable. Any problem with this? Ah. Recapping, assume that B is countable. So you have bijection from B to N. Now you focus on the set A. You say, hey, I'll focus on the mapping that has to do with the elements of A. This mapping has to be injective because B is injective. And there you go, you get a contradiction because A is uncountable. There's another solution. Has to do with the listing intuition. Prove that a subset of a countable set is also countable. A subset of a countable set is also countable. Contrapositive. It's the contrapositive of part one. So, yeah. But it's also nice to see if you could have done a proof on your own for this. Okay. Since they didn't mention, hey, you can't use this idea, so you used it. Okay. I think that's all of assignment 4. If you have any questions, let me know now. Like I mentioned, this week in recitation 6, we're gonna be working on induction mainly. So a whole bunch of new ideas. Make sure you're very comfortable in sets and functions and cardinality. before we move on to the new ideas. Okay, so I'm gonna end the meeting in a couple of minutes in case anybody wants to ask something. Otherwise, we can go now. You're welcome.